Kia ora, Year 12 and 13. Here's the last excellence question from the 2013 paper. This is a related rates question about a spherical balloon being blown up with helium. So you should be thinking chain rule, and that's what it's going to be. Alright, a spherical balloon is being inflated with helium. The balloon is being inflated in such a way that its volume is increasing at a constant rate of 300 cubic centimetres per second. The material that the balloon is of limited strength, and the balloon will burst when its surface area reaches this amount here. Find the rate at which the surface area is increasing when it reaches bursting point. So we're looking for this derivative, dSA by dt at bursting point. As I've said lots of times now, don't worry about figuring out when that is and substituting until the very end of the problem. So what we've got to think about is what's the volume. Well, we've got dV by dt is equal to 300. We might as well write down an expression straight away for the volume of a sphere. Right, so that's equal to 4/3 pi r squared. And the surface area of a sphere is given by 4 pi r squared. Okay, so we are looking for the derivative of this with respect to time. So I'll do that on a new slide. Okay, so we want to find dSA by dt. We know it's going to link up those three things: time, surface area, and volume. Now we know that we've got dV by dt, and we're going to have something linking, well, what's surface area is a function of the radius, and volume's a function of the radius. So the chain rule stuff is going to go like this. Right, so how does the volume change with time? That's this one. What's the link between the volume and the radius, and what's the link between the surface area and the radius? So dSA by dr is equal to 8 pi r. Right, remember from the last slide, surface area was 4 pi r squared. Sorry about any background noise. Hope it's not too bad. Now we've got dV by dr is also really easy. dV by dr is just 4 pi r squared, which you might notice is equal to this. Let's not go into that right now, but it is. We don't want dV by dr, we want dr by dV. So dr by dV is just 1 over 4 pi r squared. And so now we're good to go. So dSA by dt is equal to the first one, 8 pi r times 1 over 4 pi r squared times 300. Right, I think you have to agree that for an excellence question so far, this really isn't that bad. Now we're going to simplify out, and we're going to get 2 over r times 300, which is just 600 over r. The last thing we've got to do is to figure out what value of r am I substituting in. So bursting point means the surface area is equal to 7,500 squared centimetres. So we're solving 7,500 is equal to 4 pi r squared, which is a year 10 algebra problem. So we've got r squared is equal to 7,500 over 4 pi. So r is equal to plus or minus 24.43 centimetres. Right, just a wee note up here. Ignore the negative solution, 24.43 centimetres in this context. Okay, we need to have a positive value of r. So it's worth saying something like that just to communicate why you're just ditching one of those two solutions. So I haven't quite finished. That's my radius where the balloon's going to burst, and I need to substitute that into my expression for the rate of change of surface area. I'll do that on the last slide, but most of you probably aren't going to bother watching it. Anyway, here it is. dSA by dt is equal to 600 over r, which is 600 over 24.43, or 24.56, And my unit here is going to be squared centimetres per second because I'm working with surface area. Okay, that's all for now. That's the 2013 paper done. I think you've got to say that the 2015 questions were a step up from the older excellence ones, but we'll see what happens this year. Thanks for watching.